Mastering artificial neural networks. Artificial neural networks harness the trifecta of data, algorithms, and architecture to wield predictive power. Which essential elements comprise the architecture of an artificial neural network, enabling its ability to learn and make predictions from data? The architecture of an artificial neural network, ANN, comprises several essential elements that enable its ability to learn and make predictions from data. These elements work together to form a complex system that can learn, reason, and make decisions based on input data. 1. Artificial neurons, nodes or perceptrons. The building blocks of an ANN are artificial neurons, also known as nodes or perceptrons. These neurons receive one or more inputs, perform a computation on those inputs, and then send the output to other neurons. Each neuron has an associated weight, which determines the strength of the connection between neurons. 2. Layers. Artificial neurons are organized into layers, which process and transform the input data in a hierarchical manner. The most common types of layers are: input layer, receives the input data and passes it to the next layer. Hidden layers, performs complex representations of the input data, allowing the network to learn and abstract features. Output layer, generates the final predictions or outputs based on the input data. 3. Connections, synapses. Connections, also known as synapses, are the links between neurons that enable the flow of information from one neuron to another. Each connection has an associated weight that determines the strength of the signal transmitted between neurons. 4. Activation functions. Activation functions are mathematical functions used to introduce non-linearity into the neural network, allowing it to learn and represent more complex relationships between inputs and outputs. Common activation functions include sigmoid, ReLU, rectified linear unit, tanh, hyperbolic tangent, softmax. 5. Forward propagation. Forward propagation is the process of passing the input data through the network, layer by layer, to generate the output. Each neuron receives the output from the previous layer, performs a computation using its weights and activation function, and then sends the output to the next layer. 6. Backpropagation. Backpropagation is an essential algorithm used to train ANNs. It computes the error gradient of the loss function with respect to the model's parameters, allowing the network to learn from its mistakes and adjust its weights to minimize the error. 7. Loss function, objective function. The loss function, also known as the objective function, measures the difference between the network's predictions and the actual output. The most common loss functions are mean squared error, MSE, cross entropy, binary cross entropy. 8. Optimizers. Optimizers are algorithms used to adjust the model's parameters to minimize the loss function. Common optimizers include stochastic gradient descent, SGD, momentum, Nesterov accelerated gradient, Adam, Prop. 9. Bias and weights. Bias and weights are the learnable parameters of the ANN. Weights determine the strength of the connections between neurons, while bias terms shift the activation function to capture more complex relationships. 10. Regularization techniques. Regularization techniques help prevent overfitting by adding a penalty term to the loss function. Common techniques include L1, ReLU, regularization, XYZ, ridge, regularization, dropout, early stopping. These essential elements work together to form a complex system that enables an artificial neural network to learn and make predictions from data. By combining these elements, ANNs can learn to recognize patterns, make decisions, and solve complex problems in a wide range of applications.